In the earlier lectures, we saw about measurements, right? What is that? Because we said the physics is basically quantitative science. So quantitative science means we should give a number. Okay, so when we want to give a measurement, so we always give a reference to some measurement, and that we call as a units. And then we define the fundamental quantities, which gives the fundamental units. Then what are the derived quantities, which are derived units, and then we found the dimensions. Okay, the dimensions are when you express in terms of the fundamental quantities. That's what dimension comes. So we did all these quantitative measurements in physics. Now, when I say a quantitative measurement. So for example, I have a rod. I'll say what is the length of the rod. So I can say, okay, the length of the rod is typically 10 centimeters. Now the question comes, how much are you sure about it? You are saying that 10 centimeters is accurate. Okay. So when you say, are you sure this is a 10 centimeter? Is there anywhere 10 centimeter plus minus some inaccuracy is there? I'll ask a question, is it really 10 centimeter or it is 9.9 centimeter or 10.1 centimeter? Or 10.01 centimeter or 10 centimeter? Okay, so that is a small precision I will not be able to tell you. Okay, so that this inaccuracy, we will not be able to give a measurement, means we will not be able to give a very precise measurement. All our measurements will have a bit of inaccuracy. Sometimes inaccuracy will be very, very small. Some places inaccuracy can be very large. Okay, so because of this inaccuracy, your measurement is going to be erroneous. Erroneous means it's not erroneous. It will have a small component of error in it. Okay, so when I say it is 10 centimeter, it may not be exactly 10 centimeter. It may be 9.99 centimeter. Okay, or 9.99999 centimeter, not be 10, or 10.0001 centimeter. So I will not be able to differentiate the very finer thing. Okay, that is because of my instrument. Because for example, if I'm using a scale, we know the scale, the least count is 1 mm, that is 0.1 centimeter. So if I want to ask you, can you find out anything less than 0.1 centimeter or say 0.01 centimeter? You will not be able to get that measurement with that precision using a normal scale. So all quantities which we are measuring in physics, they are not going to be exact. So there will be always a bit of inaccuracy in the measurement, and that inaccuracy gives rise to some errors. Okay, so and that's what we call in the errors in measurements. So this, when we say the errors in measurement, this has basically broadly come into two types. One is systematic error. And other one is random error. So let us see one by one what do we mean by these errors. First we will see what is a systematic error. So systematic error is something, it's more largely to do with our experiment what we are doing. Okay, let us try to do an experiment. Okay, so I am going to do an experiment. I am having a tap with a lock. Okay, so I am having a beaker, say something, measuring beaker. So I am going to, so the let experiment is, I want to say how, and this, let us assume the water flow in this pipe is constant, is not going to change with time. I'm asking you a question, in 10 minutes, how much water will be collected in the beaker? So it is a measured beaker. So this is the question I am asking. This is the experiment I am going. I want to measure out in 10 minutes how much water will be collected in the beaker. So what's my experiment? So I have a tap with a lock. If I press, let us say if I press it, it stops. If I pull it, it opens. Okay, so and there's a beaker. It may be measured beaker, maybe cylindrical beaker. So I know, so cylindrical beaker, so I can always find out the volume. This is the area of the base into the height of the water level. So now, when I do this experiment, so I am going to say, okay, typically I will say in 10 minutes, it collects 2 liters of water. Now, this is not going to be exact. The reason is, it may not be 2 liter, it may be 2.1 liter or 1.9 liter, because depending upon my instrument. Because see what happens, so I'm going to tell you are going to do the experiment, right? So you have to start the tap and close the tap at exact 10 minutes. But there can be a delay in your point. So you wouldn't have stopped at 10 minutes. You would have stopped just 2 seconds more, or 1 second more, or 0.1 second more. Or not just that, when you close the tap, the instrument will have a delay. Instrument sometimes you do stop early, or whatever. So instrument also can have an inaccuracy. And all these beaker measurements also, I may having all this inaccuracy. So this all is going to cumulatively give me some error in my experiment. Okay, so this error, you call it as a systematic error, because it's depending upon the experiments and the experimenter. Okay, this is error created by the experimental setup as well as the experimenter himself. Okay, so and typically this error is what are the typical components of this error? What are the components of the error will come? So the first component is the instrument error. What is instrument error? Instrument error is because of the poor quality of instrument you are using. The instrument may not be exact. Okay, so what is the error I told you? So the point is, when I want to stop the cork, when I want to stop the flow, the instrument will not exist. My assumption is when I press it, it stops instantly. But instrument may have a delay. Okay, it may not take it. Still, it would have let some water. When I push it off, at the time it should cut the water, but it will slowly release some water. Okay, so that means that is having an error. Similarly, this beaker, this measurement may not be accurate. Okay, that means I am using a scale, right? So if I am using a normal scale which is accurate up to 0.1 centimeter, but if the water level is slightly above 0.1 centimeter, I can't find out the value, correct? So that is also going to be an error. So this is an instrument error. The instrument has some limitations. Okay, so this error, which we call as the instrument error. And the next one is, and this is a part of systematic error. And second part is, what is the error due to imperfection? Yeah, correct. Which basically, let's say something like your experimental technique. So what is the experimental technique? See, your instrument may have some error. Okay, added to it, your experiment also may have an error. Experimental technique. Now, what is the example you can give? For example, yeah, okay, so this is supposed to be exactly horizontal. Am I right? So this level will be. Suppose if you have a very mild tilt, okay, which is not horizontal, then what happens? The water level is not going to be horizontal. At that time, if you measure the height here as well as the height here, this is going to be different because your water level is tilted. Okay, you measure it from base or somewhere else. So then you are not exactly calculating as a right circular cylinder. You will have something as a tilted cylinder you have to calculate. So this is another type of this is error. This is not because of your instrument. This is because of your experimental setup technique, what you are doing. Or similarly, when you close the water, you use manually with the hand. So that's all. What is the experiment technique you are going to use it? All these things will introduce an error. So that is what we call as a experimental technique error. And the final thing error is something is very interesting. They call it as it's called as a human error. but in your book they written as a personal error. Or human error. Human error is a very important part of all the errors. So the human error is what happened. For example, yeah, you are supposed to, I told you are supposed to stop at 10 minutes. Okay, so you are seeing the watch, and the watch, if suppose it's a clean sweep, that clock, okay, not that digital clock or something. So you never know when it is reaching that exact 10 minutes. Okay, so by the time I press it or something, you would have left some half a second or 1 second. So that isn't going to be an error you introduced. Okay, and while I'm measuring the level, if you remember the parallax, you have a scale, you measure it like this or measure it like this. There's going to be a slight shift in your measurement, right? So this is going to give, it is because you are supposed to measure all the scales. When they give the scales, how do you measure? Supposed to measure exactly vertical. But there can be a slight parallax because of the way of taking the reading. So, and those things can give rise to some error. Okay. So that's because of the human, because it's the inability to read properly or start the experiments properly, or some error because of the humans. Okay, we are not able to handle it. So this error is called, this three are personal or human error. So these three errors contribute to a systematic error. Okay, so there is a way you can reduce these errors. How you can reduce error? For example, instrumental error. Simple, you use a better instrument. Okay, so what am I going to do? I am not going to use this cock side with the hand or something. I will make an electrical. I'll give a supply and I'll pick a relay or something, whatever, and there will be one remote here, and then that is going to act as a lock. Okay, so in that case, what happened? So I can, when I have the remote, when I exactly press, it stops immediately. Then the human intervention has reduced. Okay, so that would have reduced, and this, human intervention, the instrumental delay, I would have reduced, I have made a more precise digital lock. And, or even if to avoid it by pressing, I make it automated. I set up, program it at some time, it starts and stops at exact time. So that time it is going to be more precise. So I can do more and more techniques, advanced setup, advanced instruments to make it more precisely open and close the water. Similarly, this beaker. I can have a beaker with a very precise measurements. Okay, so it's whose least count is very, very small. You know what is the meaning of least count, right? Least count is very small. Then I can always measure the height of this water also precisely. So what happened? So by this, I can actually reduce my instrumental error. What about experimental technique? Keep it, make the experimental technique proper. Okay, that's why in say experimental technique, what happened, instead of me going and closing the lock or something, you make it all electronic. Okay, and you make the experiment, means you have to, the response of the system will be very fast. Okay, and this level, everything I make it perfect. Okay, so there's the experimental technique should not have any flaws. So I can reduce the flaw, I can make the level properly outside, and this water, how to close and everything, all this, the way I'm going to do, I don't use this very primitive method, I will use a high technology used to do the method. This is one example I'm giving. Okay, so that way also I can reduce my, the error due to my experimental technique. Human error, simple. You have to go for a careful reading. You can't go for an arbitrary reading. If you are very seriously doing the experiment, taking a proper measurement, then your human error is also going to be reduced. So this error, somehow this systematic error, which is a part of these three errors, I can make it my instruments, everything precise, and a very hi-fi setup techniques, and a very attentive lab assistant or someone, so that I can make this experiment more and more precise. I can reduce the systematic error. Okay, but the second component of the error, this is something you have to live with it. What do we mean is, I have made up a system. It's a very precise system and everything. It is going to be exact. With all these errors are very minimal. Still, this random error is going to be there always. What do we mean by random error is? Suppose I am asking you to do this experiment with this precise setup. I am asking you to do this experiment some 10 times. So, will you get all the 10 times the exact, suppose your measurement it gave 2 liter in 10 minutes, 2 liter. This is the, when you do it for the first time. Second time, 10 minutes, you may slightly differentiate 2.001 liter. Okay, third time, 10 minute, 1.999 liter. So if you do that, if you keep doing these experiments again and again, you may not get always the same. There will be whatever you try to build up this reduced systematic error, always there will be some inaccuracy which comes out. Okay, and usually this reason for this inaccuracy is something which is beyond your control. The reason why this happens is, see, because when you do the first time, 10 minutes, that's a different time. And when you do the next 10 minutes, that has changed. Your system has completely changed with new time. For example, you are doing this experiment from night to afternoon. The night, your temperature is very low. The daytime, your temperature is high. It may happen your pipe, metal pipe, okay, where the water flow is coming. During the daytime, the pipe expands very small and little, but it has expanded very small. So the water flow has been changed. So these are all the environmental things which is not in your control. You can reduce most of things, but something or the other will come up. Okay, or if you are doing electronics experiment, some battery fluctuations, something, whatever you do, some spikes or something, okay, some surge current has come and all. So these are all going to create an error. So, and that error is called as your random error. Okay, and remember these errors can be actually, if you see here, they can be actually positive as well as negative. Okay, so it can be both the ways. So now, so in physics, when you are doing an experiment and when you are giving a number, that's a quantitative science. When you are giving a number, you should always, along with that number, you should always give the error in your calculation. That means this number is accurate up to this level. Suppose if I say 2 liter and I say 2 liter plus minus 0.1 liter. So 2 plus minus 0.1 liter. That means if you do this experiment some 100 times, you will find that the most of the time, almost all the time, you can say the water collected will be 1.9 to 2.1. It should always fall within this range. You can see 2 minus 0.1 is 1.9, 2 plus 0.1 is 2.1. So this is the correct way of giving any measurement in physics. So this experiment I said it of my own. In your book they are given something different. Okay, so let me read some of the lines in the book so you can actually connect what I am saying. The systematic errors. Systematic errors are errors that are determined by chance, that are not determined by chance but are introduced by an inaccuracy, either the observation or measurement process. Am I right? That's what we are doing that. Okay, and the systematic errors can be, there are 3 types. Instrumental error. What is instrumental error? This type of error is due to the defective calibration of an instrument. For example, incorrect zeroing of an instrument. This is very interesting. Zero. See, for example, they given an example of a thermometer. So a thermometer, when you measure, suppose it's given degrees Celsius. When I put it in ice, it should be 0 degrees Celsius. But when you put it in ice, it may not show 0 degree. It may show some value. Okay, so now that inaccuracy is going to be there even when I put a thermometer in a boiling water. It is not going to, even though it shows 100 or any boiling liquid, if it shows some 80, it may not have a 80 degrees Celsius. It will have some error because your 0 degree is not accurate. Okay, so that's the one part. And other thing is your balance, the laboratory weight balance. So when there's nothing is there, it's supposed to show 0. Okay, so but it may have some small value it will show. These are the experiments they going. Yeah, this is one of the very common thing is the ammeter. You have seen ammeter in your lab? So when you want to measure a current, if you see when you switch off, this is very common in all our labs, ammeters will be pathetic. It will not show 0. It will have it will go either below 0, okay, or it goes slightly above 0. It stops there, okay. And if you actually see the ammeter, there is a backside, there is a screw. If you rotate the screw, it actually to set your 0. Most of the times in the school labs or in the college labs, those ammeters are not set properly. So all your calculation is going to have that error, okay. These are basically this is the instrumental error. This is the instrument error. Fine, and that's the one thing. Second, error due to imperfection in the experimental technique. This is error due to the defective setting of an instrument. For example, the measured volume of a liquid in a graduated tube will be inaccurate if the tube is not held vertical. Yeah, as I said here. If it is not vertical, if it is slant, so then you are going to have an error. Okay, so that's the one thing. And the final thing is a personal error. Yeah, that's what I said. Such error is due to the fault of the observer, bias of the observer, carelessness in taking observations. For example, the same thing ruler he gave when you have a parallax. So these are all the errors which comes under systematic errors. So systematic errors can be minimized by using correct instrument, following proper experimental procedure, and removing personal error. These three can be handled. Then they are coming to the random errors. These are the errors which are introduced even after following all the procedures to minimize the systematic errors. This will remind this error. Okay. So, and these errors can be positive or negative and all. See, they're written nice later. The random errors occur due to the variation in the conditions in which experiment is performed. Okay. So, for example, temperature may change, pressure may change, because you at different situations, when you are going to repeat the same experiment again and again, it's not going to happen at the same time. Or if you want to do the same time, you have to make the same type of setup. And nothing is same always. There can be always difference. Either you use the same instrument multiple times, then you are going to do it at different times. So there will be something of a wear and tear will be there. If you have used it so many times, something will change. Okay, so those things are all. These are all what you call your, this all gives rise to a random errors. Okay. So, fine. So, next, okay. So when I doing some experiment and when I going to give us some value, that value is always going to have some error. Okay. So, in physics, important thing is, do you have the measurement of that error? So, you are not supposed to give only 2. You should give 2 plus minus 0.1. Or suppose if I have an error which I call it as some quantity, measured quantity as A, I should give plus minus say something like delta A. But delta A is the error. Okay. In physics, every quantity should be given what is the precision you are saying, what is the accuracy in which you are claiming the value you are quoting is to be correct. Okay, so this is always an important part. That's why this is a part of science. Once you don't provide this accuracy, then it is not going to become science. It is going to be something like your what? Astrology. Yes, right. Okay. So what they will do, will say, okay, tomorrow you'll get a lottery. But there is no accuracy for it. Okay, you'll win a lottery of 1 million. 1 million whatever currency is there, okay. So I can tell, okay, they can say they have some experiment, some stupid arguments they have and they will do that, okay. But that is not science. The reason is, they can't provide what is accuracy in their prediction. Will I get 1 million or 1 million plus minus 2 million? That means I may lose a million or I'm going to win a million also. Okay. So, so these things they can't give. So that's why it was not a science. Okay. Physics is, the science is something where you give a number as well as you give your confidence. This is what is confidence interval. How much confident am I? When I say a value of A, how much confident am I that the answer will be A? So I will say I am confident within this error bar. So that makes science, this physics a part of science. Okay? Estimation of error. So in the what we saw, whenever I am going to do an experiment, I am going to get a value. Okay? And say for example, the same water experiment, what you are filling the water in a bucket. Nobody is going to do this stupid experiment ever in their lab. Okay, okay. So this is our thought experiment. Okay, so you can do it in a bathroom. Okay, so let us assume for this experiment. So I said, so you collected in 10 minutes 2 liters of water. Okay, in the bucket you measured, it came out to be 2 liters. Well, now I am asking what's the error. What you will do, how to get the error, there's no other option. You have to do the experiment repeatedly. Okay, so then there are 2 questions comes. So if I am so angry on you and I make you to do the experiment, do it 100 times or 1000 times. Every time you fill for 10 minutes and measure, 10 minutes and measure, 10 minutes and measure. Every time you are going to have a different numbers. But they all will be close to 2, correct? Sometimes you may get 1.9, sometimes you get 2.1, sometimes you get 2.01 or 1.99. You get many values. Okay, so and there are times sometimes the same number may repeat also, 2, 2, 2 or something. Okay, so then the question comes, when you do this experiment for 1000 times or 100 times, what is the most probable value you are getting? Okay, and the most probable value that you will study in those in your later classes. So I can say, but you have done this histogram and all, right? So let us try to do. So what happened? You have done this experiment 100 times. So you got some measurement like, so you got 2, 2.1, 2.01, 1.9, 1.99, and you go on like that for 100 times. So then you can make the frequency distribution table. Am I right? 2 to 2.1, 2.1 to 2.2, or 1.9 to 2, 1.8 to 1.9. You put up the frequency distribution. You remember that in your last 10th standard you had a frequency distribution table, right? You put the class interval. Am I right? Interval, whatever it is, interval, and then you put the frequency. You write down the frequency here. Okay, so then you do that, right? And then what you will do is, if you do the same thing for this experiment, and you suppose you take out the interval as 0.01 or 0.05 or 1, whatever class interval, depending upon the range of values, you can divide this distributions. What you will see, if your actual measurement, if it is 2 liter, what you will see, suppose this is 2 liter, 2 liter, that means it will be some class interval, maybe something around 1.99 to 2.01. Okay, so you would have got some, say something like, oh, okay, let us say 40 times or 50 times. And when you go away, it will be slightly smaller. Next one, that is 2.01 to 2.003, something like that, right? So similarly here, there will be something like this. So these numbers will be reduced. So this will be, if it is 50, this may be 45, and this may be 30, and here also it may be, say it may be 32. Okay, so you plot, you will get a number distribution, something like this. When you plot this, so now if I ask you a question, what is the most probable value that corresponds to the peak value, correct? So, and what you do is, what you actually will see is, this value is nothing but the average of all these numbers. You take the average of all these numbers, that is going to corresponding to the peak value. So when you have done this experiment for 100 times, or maybe 10 times, so then if I ask you what is the most probable value, all you have to say is just do the average of it. Okay, so that means if you have done the experiment, say for example, the same water experiment we are doing, or whatever experiment you can think, measuring the current from a circuit or whatever. Okay, so you got basically got some number. Okay, what you have to do is you just repeat the experiment for some n number of times, say for 10 times, or 20 times, or 100 times, or 1000 times, depending upon how much time you have, okay, or how long you are getting bored with it. Okay, so you are going to have, so let us make it, say for example, A1, A2, A3, you did up to A10 and then you got bored of, you left it. So now the question is, so every measurement, every number, these are the numbers you got from the experiment, correct? So this is going to be slightly different. So what is the most probable value? All you have to do is you have to A mean, which is equal to A1 plus A2 plus A3 plus A10 divided by 10. Yeah, because total numbers, right? If you have two numbers, is A1 plus A2 by, what is the average? What is the average of 1 and 3? Tell me.
1 plus 3 by 2.
So 1 plus 3 by 2 how much? 1 plus 3 by 2 equal to 2. Okay, so this is the way average you define. So when you have three numbers, you have to take by 3. Suppose if you have n numbers, n can be 10, 20, 30, 100. At that time what happened? This will be n, correct? Divided by n. Okay. So this quantity, A mean, is the most probable value you should use in your experiment. Okay. So then when we did the experiment, what we found, the most probable value, when I take all these numbers, you find the average came out to be 2. Okay, so then let us write my most probable value is equal to 2. Now I said this is not complete. I have to give, so this is 2 liter is the most probable value. All I did is what? I took, this 2 is what? Nothing but the average of all these numbers. So this give me the 2 liter, most probable value. But in physics, you are not supposed to give only this number. You have to give the error also, correct? So how do we find out that error? That means 2 plus minus plus sum. Error can be both directions, as I told you. So what is the error in it? How do we find this? So this is a mean value, correct? So then there's a term called as your absolute error. What is that? Absolute error. Absolute error. Let me write it as absolute error. So what absolute error? So absolute error is, so for every measurement, there is an error in it, correct? So typically what the error I will say is how much this every measurement is going to be different from my mean value. That is my absolute error in that measurement. You got what I am saying? So every time, sort of, I had done the experiment 10 times, I got the 10 values. Okay, I took the 10 values, take the mean of the average of the 10 values, mean and average is same. Okay, mean of the 10 values, and that mean is going to be my most probable value. Okay, so now I got the most probable value. Now I am putting the question, so all my 10 times the experiments I am doing, every experiment is having some error, correct? That error I am going to call as absolute error. What is the magnitude of the absolute error? That value minus the most probable value, correct? So for example here, this value minus the most probable value. So this difference, that means, suppose if it is 2.01 and if the mean is 2.01 minus 2. Okay, a minus, you can take the difference, take the mod of it, we will not have the sign of it. So this is the way. So your absolute error in this experiment is 2 minus 2, that is 0. Absolute error in this experiment is 2.1 minus 2, it is 0.1. Absolute error in this experiment is again 0.1. We don't take the sign of it. Okay, they take only the difference of it. So this is absolute error. So absolute error for every experiment we have to define. Okay, so what will be the absolute error for, so in case of A1, what will be the absolute error of A1? Tell me. And we denote it as delta A1. Delta A1 will be what? I said difference, correct? So that will be A1 minus A mean. Am I right? That's what I have done it. Correct? Similarly, this for the first experiment I did the value. The second experiment, delta A2 will be A2 minus A mean. Okay, I can keep on doing up to, if I done the experiment for n times, I can always find the, I can easily find out the absolute error for all the n experiments. An minus A mean. So then I am going to have a collection of absolute errors. Am I right? So we are going to have a collection of absolute errors that is depending upon my mean. So when I did the 10x, when I repeated the experiment 10 times, I got a mean value, not just the mean value. I got a mean value and I got the absolute error for all the 10 experiments. So then what I am going to do, then what is my error in my mean value is the mean of all these absolute errors. Okay, so what will be the mean of absolute error? So what is the term called? Yeah, mean absolute error. They call it as a. So, and that is, so mean that is, we write it as delta A mean will be equal to, so these all are positive quantity because we are taking only the difference mod of it. Okay, so that will be delta A1 plus delta A2 plus delta AN divided by n. I forgot to write. This can be written it as, you know that my symbol form, right? 1 by n into summation of I equal to 1 to n A of I. Correct? So similarly we can write for here as 1 by n summation of I equal to 1 to n delta A of I. Correct? So this is my A mean. So now I have done the experiment for 10 times. I got the most probable value, which is nothing but the mean. Then I got all the absolute errors, taken the average of the absolute error. So after the 10 times I did the experiment, I will say the value I got is the most probable value, that is A mean. Okay, and the uncertainty or the error, the inaccuracy in it is plus or minus delta A mean. Okay, so you remember this delta A is always positive. We take only the magnitude, isn't it? So this will be always positive. So we have tried this can be either positive as well as negative. Am I right? So this gives you a complete description of, when I giving a complete description of the value I have obtained from the experiment. Okay, so this is, when you get this number and complete it, that finishes that is the proper result of your experiment. Okay, fine. So that's what they have done. Yeah, and the next one is, okay, so okay, so this is your, so we got this, so this is the most probable value and the error in the probable value. So now, okay, so I am having two experiments. Let me say I am doing the two experiments to find out the same quantity. Okay, for example, let us take the current through and resistor of certain resistance and on a voltage or something. I am going to do the experiment. I am going to give the experiment, make the experiment to be done by two different people, and they don't communicate with each other. They both are going to have a different instrumental setup. Someone must have used some better experiment, some better ammeter. Someone is a poor quality ammeter, or the guy who was using the better ammeter would have used a very poor quality resistor, which is not accurate. Okay, so then the current is, then what happened? All they have to do is they have to do the experiment for 10 times or 100 times. Give me this value. Now I am asking you a question: whose value is more precise? You got it? So when I come for whose experiment give me a better precision answer, then there comes what you call the relative error. Okay, so the relative error is an interesting quantity. So what is that? Relative error is what's the relative error? Is delta A mean by A mean. Okay, do they have a symbol for that? No, they didn't have a symbol. So this is what they call relative error is this one. Okay, so this is how this is going to give me the measurement of relative error. Suppose, for example, so there are two experimenters. Okay, so experimenter 1 and experimenter 2. Okay, the experimenter 1 gave me an answer. So for certain experiment, the current or whatever the experiment, he gave me an answer with a number something like, say for example, 5 plus or minus 0.1. And the other person, okay, and did other experiment. Okay, so then he gave me an answer 5 plus or minus 0.2. So from here itself you can say this is which is more precise, but when the numbers are different, okay, then you can't tell out of for some different experiments for different current, different values of current. So one value is given as 5.1, the other person is doing completely new experiment with a new measurement of current. So he got some other value. Okay, but he got something around 2 plus or minus 0.1. Or say something like plus or minus 0.2, for example. Okay, so now I am asking which experiment is precise. So the point is you have to take out delta A. So this is your most probable value. So if you remember what we said, the most probable value is the first we write, right? A mean, and this is your delta A mean. Am I right? So when you want to do the relative error, what happens here? You tell me. So this will be what? Delta A mean by mean. That means 0.1. In this case, relative error is 0.1 divided by 5. And here it is 0.2 divided by 2. What is this value? Tell me.
150, which is 0.002.
0.02. Correct, na? This will be?
0.01.
Which is smaller.
Yeah, 0.02.
This is right. So this experiment is more precise than this experiment. So this gives you an idea of a relative error. That's what relative error. But usually if you remember, these errors are going to be smaller. Okay. So then, suppose somebody gave an experiment of what is it? 2 plus or minus, my error is also 2. Okay. In this case, error is what? So your A mean and delta A mean. This is the worst case experiment. Okay. So what happens? So equal 2 divided by 2 equal to 1. Okay, and so this is the worst experiment you have done. Okay, so this has to be always smaller and smaller. Okay, and as I said, so this is a very small numbers, right? So usually what they call, they write is the percentage of the relative error. What do we write? Percentage of relative error, or simply they write percentage error. Okay, either of them you can write percentage of relative error or percentage error. Percentage error is nothing but your relative error multiplied by 100. That is delta A mean divided by A mean into 100 percentage. So in this case, what will be? Tell me, relative percentage will be 2%. And this case, 10%. And this case, 100% error. Very good. You got it? So this will give me how this. So this is give a nice measure. Okay, that means my experiments are accurate up to 2%. My experiments are accurate up to 10% accuracy. I am claiming. When I do the experiment, I can claim my experiment is so precise, its accuracy up to 10% accuracy. So this is one of the nice way of defining the precision of your error. Okay, so relative error and the percentage error.